We've learned already that atom is made up of even smaller constituent particles, which is pretty amazing because atom is an unimaginable small particle by itself. Those particles, nucleons, are protons, heavy nucleus located and positively charged. You already know this. Neutrons, heavy nucleus located and have no charge at all. And electrons, negatively charged, must consider to be equal to zero because they are very, very, very light. However, it is the electrons within the atoms that determine the physical and chemical properties of the elements. To understand properties of an element, we need to look at the arrangement of electrons within the large volume around nucleus. Negatively charged electrons attracted by positively charged nucleus. They don't fall on the nucleus. Why not? Because each electron has certain amount of energy which allows it to stay far from the nucleus. Let's say energy it's like money or independence. If kids don't have money, they stay near to parents, right? If they do have money, they can move farther from parents, just like electrons. If they have vast amount of energy, they locate far from nucleus. Let's say this is nucleus, right? And electron with high level of energy can be located. It can locate here, right? Electron, and electron with small amount of energy will locate here, closer to nucleus. Thus, electrons with approximately the same amount of energy hang out together. The maximum number of stable levels in an atom where electrons can be located is 7. This diagram, this picture shows you the visualization, how levels can be located compared to nucleus. Just like the number of periods in the periodic table, which are 7, 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. 7 periods in the periodic table, and there can be only 7 stable levels with electrons in atom. They numerated from nucleus 1 is closest one, and the 7 is the farthest one. Indeed, the elements of the first period have only one electronic level with electrons. That is, their electrons have a very low energy. The elements of the second period have 2 energy levels with electrons and so on. Levels we will be calling shells. In a stable atom can be 7 shells or 7 levels. For some of you who are going to take chemistry 1 or chemistry 2 and so on, it's good to know that electrons can jump from shell to shell. This diagram shows us this. If electron absorbed some energy, the certain amount of energy, it can jump from the higher level, higher energy level. If they release energy, it jump back. Each subshell, each shell contains subshell or sublevels. Sublevels or subshells can be S, P, D, or F. Electrons orbit around the nucleus, but not like planets orbit around the sun. That's not the case. Electrons are not in these well-defined circular or elliptical orbits. In fact, at any given point in time. It's not necessarily exactly there or there. It could be there, but it can be everywhere. So if this electron can be here or there or there or there or there, but inside this shell, right? That is why we can talk about only a probability. If electron has certain amount of energy, it's likely to be found on a shell with this energy level. That's why physics and chemists introduced the idea of an orbital instead of orbits. So each subshell contains orbitals. Just to make it easier, if we imagine atom as a mini apartment building, our shells would be floors, subshells would be apartments, and orbitals would be rooms. An atomic orbital is the region of space around the nucleus of an atom where an electron is likely to be found, highest electron density. So S electron, which are on subshells S, likely to be found on an equal length distance from the nucleus, which is spheric, right? P electrons, which are on sublevels P, orbit on the very strange how to say orbitals, which is P. It can be like this. So electron can be or here or here. This is nucleus here, right? So we can find we can mostly probability the most probability to find this p electron is to find it here or there. Closer to nucleus, less probability to find p electrons here. And p electrons can be on 3 different orbitals. As you can see, S electron has only one orbital, which is spheric. P electrons have 3 types of p orbitals, which oriented horizontal like this, or vertical, or how to say in and out, I believe in. D electrons has 5 different orbitals. F have more than 5, even 7. There are certain rules of how electrons occupy subshells and orbitals. The Aufbau principle, it's a very strange name, comes from German, it's like building principle, states that in an atom, electrons fill atomic orbitals of the lowest available energy levels before occupying higher levels. That makes sense, actually. Just fill out the low energy levels, and if they have no space anymore, you can climb higher and higher. For example, 1s level is filled before the 2s sublevel is occupied. It makes sense because we can see 1, the first level, stay closer to nucleus. That means that it has lower energy than the second level. There are certain rules how electrons occupy subshells and orbitals. Aufbau principle. This name comes from German. It's like building principle. States that in atom, electrons fill atomic orbitals of the lowest available energy level before occupying higher levels. For example, the first level is filled before the second S sublevel is occupied. This is order of subshell filling, right? So we can, okay, I can write here, perfect. Can I? No, I cannot. Okay, but anyway, so we can try to write down the order for each element, how they are built. Okay? Please pay attention to this order. This is order of increasing energy. It says that the first level being filled is 1s, the second being filled is 2s, then 2p, 3s, 3p, 4s, and so on. Pay attention to these red ones: 3d, 5s, 4d, and so on. So there is a Pauli rule also. It states that each orbital can hold a maximum of 2 electrons, and these electrons must have opposite spins. So what does that mean? I want you to take a look at this picture. Yeah, here it is. This picture. It shows us that first shell has only one subshell, right? First shell, one subshell, which is S. S subshell has lowest level of energy all the time. The second shell has two subshells. The lowest one is S, and higher level for for second shell is P subshell, and you can see it, right? Third shell has three subshells S, P, and D, and D higher by its energy than P subshell. Four shell or four level has four subshells S, P, D, and F. And more complex is about fifth shell, so it has 5 subshells. And this is arrow which shows us energy increasing from the first shell level, from the first shell energy to fifth shell energy. Okay. So orbitals. Back to orbitals. Every subshell has a certain amount of orbitals. S always has one orbital, and each orbital on each orbital can be only two electrons, but they cannot be the same, exactly the same. At least they need to have opposite spin. What does that mean? Spin. The electron orbits around the nucleus, and at the same time it orbits around itself. So it can orbit clockwise or counterclockwise. So that means spin. Positive spin when electron orbits clockwise, and negative spin is when electron orbit or moves counterclockwise. So S subshell has only one orbital with maximum 2 electrons on it, right? P has 2 electrons in each. That means 6 electrons. We can write it down here together. So 2 electrons here, maximum 2 here, 6 here, again S subshell, 2 electrons, P subshell, doesn't matter, 2p or 3p or 4p, it will be 6 electron, right? For S, 2, the same, 3d, D has a place for 10 electrons, right? So, and you can see 3d or 4d, it will be 10 electrons. P, the same all the time, 4p, 6 electrons, 5p, 6 electrons, 6p, 6 electrons, and so on. And pay attention to F. F subshell has 7 orbitals and 14 electrons can be located, the maximum amount. And let's go back to our wow principle. Order of subshell filling. The first of all being filled 1s orbital, maximum 2 electrons here. And you can see 1s. So let me explain. What does that mean? 1s, right? And we can see 1s2, for example. 1 means shell. S means subshell. Sub, oh my god, sorry, subshell. And 2, amount of electrons. How many electrons on this exact orbital? Okay, so 1s, maximum 2 electrons on it. Then if it has no place for electrons no more, the next electrons has to climb on the level with higher energy, which is 2, which is second. So second level start filling with S subshell, 2s, then 2p, right? So 2s has place for 2 electrons, and 2p has place for 6 electrons, right? So on the second shell can be maximum 8 it's in Russian, I'm sorry, 8 electrons. Here, 2 electrons here. Okay, so third shell, we can see third, it has S, P, and D subshells. 2 on S, 6 on P, and 10 on D. Together 18 electrons, maximum amount of electrons which can be on the third shell, right? But this is a kind of tricky, right? You can pay attention. What does this arrow mean? The first one shows us that the first electrons goes on the first shell, on the first level, right? The next amount of electrons go on the second, but then after 2p, 3s being filled, right? Okay, but 3p after the next one, and instead of going on 3d, next electrons goes on 4s subshell, okay? And 3d fills after 4s is finished. And here on this diagram, you can see that D 3D level, 3D subshell, it has higher energy level than for S subshell. Okay, and maybe this row will be easier to use. It has the exact order of increasing energy, and it has exact order how electrons fill shells and subshells and orbitals. To track electrons in an atom, chemists use an electron configuration. And electron configuration simply lists the levels and sublevels or subshells labels, which writes superscript given the number of electrons in that subshell. The shells and subshells are listed in the order of filling. Let's do these together. We will be jumping from this to periodic table, right? Why do we need periodic table? Because I want you to see what is the atomic number, what is the period number, okay? So the first one is hydrogen. So jump to periodic table and it shows us that hydrogen has atomic number which is 1, right? Which is 1. So 1, it has 1 electron, right? And it stays, it locates in the first period. So that means that it has only 1 shell, right? And 1 electron on 1 subshell, which is S. That's why its electron configuration we write down like this: 1 S 1, correct? And let me rewrite it here: 1S, then 2S, then 2P, then 3S, then 3P. Yeah, okay, it's enough for this part of the table. And that is like this. The next one here, you can see it's atomic number 2, right? So we put it here, atomic number is 2, that means it has 2 electrons, right? And still the first period, that means the first level, right? And you remember that on S subshell it can be only 2 electrons, right? But hydrogen has 1, so there's a place for another one. So helium has 1s2. That means that on the first shell, on S subshell, it has 2 electrons. Okay, the next one, lithium. Yeah, here it is. Atomic number is 3 electrons, and it's already filled. The first shell already filled, so it will be 1s2, like helium has, right? But the next electron, the third one, goes on the second shell, and you can see 2s, and amount of electrons there, it will be 1. So its electron configuration is 1s2, 2s1. What does that mean? Let's say it again. Lithium has 2 shells, the first and the second, because it's the element of second period, okay? And on the first shell, it has 1 subshell, 1s subshell, and 2s electrons there. and on the second shell it has S subshell and 1 electron there. Okay, let's do that the next one. So just you can see beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, so 4, 5, 6, 7, 8, 9, 10. Okay, yeah, I need this row to be visible. Okay, so beryllium has 1s2, 2s, the same as lithium, but it has 1 electron more, and it goes on a S subshell on a second level. Okay, so beryllium configuration is 1s2, 2s2, and you will read it like this. Okay, boron, its atomic number is 5 and its electron configuration will be 1s2, 2s. Can it be a 2s3 or not? Okay, so it cannot be 2s3 because on S subshell can be only 2 electrons, not 3, only 2. Maximum amount of S electrons on each shell can be 2. Okay, so 2s2, and but we need 5 electrons here. Where to the next electron go? 2p, and you can see here 2p, so it will be 2p1. Okay, carbon 6, 1s2, 2s2, 2p, 2, of course, it's easy, right? And nitrogen 7, 1s2, 2s2, 2p, and there is changes. There are changes here, right? Not 2p2, but 2p3, right? And oxygen, the same, 1s2, 2s2, and 2p4. How many electrons can be on p subshell? 6. It can be 6. So we still have place for 2 more, right? And fluorine, 1s2, 2s2, 2p5, and neon, 1s2, 2s2, and 2p6, right? And it's done. Okay, so it's done. No more electrons on 2p subshell, right? No more electrons on second shell because it's already 8, correct? So, and as you can see, these electrons on an out shell when there are 8, that means that this atom is very stable. It's very stable. It is not. It reacts with anything, so it is stable. Because if an atom has less electrons than 8 on its outer shell, right? That means that this atom can react with other elements to get electrons, and we will be talking about that later on. But anyway, so just pay attention to these 8 electrons. And do you remember what is the name of this group where neon and helium are? Noble gases. Why they're noble? Because they have zero ability to react. Okay, let's go further. Potassium. Potassium, let's find it in periodic table. Potassium, it's number 19. So it has 19 electrons, and period number is 4. Period 4. That means that potassium's electrons will be located on 4 shells. Okay, so, and let me rewrite the order: 1s, then 2s, then 2p, 3s, 3p, then 4s, then 3d, and then 4p. This is the order, and we do not forget that as subshell has only can have only 2 electrons. P subshell can have only 6 electrons maximum, and D subshell can have a maximum 10 electrons. So let's jump to potassium. Okay, 1s2, 2s2, 2p6, like neon, right? But it has the third level, which has 3s subshell and 3p subshell, right? So 3s can have maximum 2 electrons, so it will be 3s2 and 3p6, which give us, if you add these subscripts, you will get 2, 2, and 6, 10, and 2 and 6 is 18, but potassium has 19 electrons, and where to the last one go for 4s, okay, 4s, and the last one located here, 4s. So, but just pay attention, all these elements from hydrogen to potassium located in main groups, right? Just remind you, A means main group. So hydrogen, helium, from lithium to neon, potassium 2, and all elements of the third period are located in the main groups. Okay, so but it's not like this for iron. Let's find it here. Iron here, right? So it's in B group, actually 8b. Iron, 26, its atomic number, that means that it has 26 electrons. So, and just write down its electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s, 4s. S subshell can have maximum 2 electrons, and it's 26 in iron atom. So yeah, it filled, right? And then after, electrons go on 3d subshell. So 3d, and how many electrons left? We can calculate. So we have already 20. If I add all subscripts, I will get 20 electrons. That means that on 3d subshell, it will be 6 electrons. Can you see? Okay, let's do another one. Or it's here, 32, and selenium is 34. Okay, 32 and 34. Okay, and we can do it together. as you can see, this part will be the same, right? So I just write it down like this. 3D. The maximum amount electrons on D subshell is 10. Can we have 10 electrons here? Let's add subscripts. So it will be 2 and 2 and 6, 10. Then 2 and 6, 8. That gives us 18, 20, 30, right? But there are 32 electrons in this atom. So after 3D, 4p subshell being filled. Okay, so on 4p, 2 electrons here. Okay, the next one, selenium. It can be way easier. You can pause this video and try to do it by yourself and then check it, okay? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. And if you add all subscript, you will get 32 electrons. Chemists not all the time use this long form of electron configuration. Very often they use abbreviated electron configuration, and I'm going to show you how to do that. We can start with noble gas helium. So helium, right? And the next element, we will compare it to helium. So we will say helium. Why helium? Because it has finished outer shell, okay? And then all elements which are located in the second period, we will compare them to helium. But elements from third period, we will compare them to neon, okay? And I will show you how to do that. So lithium, it will be just like helium, but the difference is here. And we write it down here, 2s2. So we can show only differences, okay? And beryllium, it will be helium and 2s2. And you can pause and try to do it by yourself and then check, okay? So helium the same, 2s2, 2p1, 2s2, 2p2, and 2s2, 2p3, and 2s2, 2p4, 2s2, 2p5. Do we need to use this abbreviation, abbreviated to? No, we don't need to, because it's the next noble gas. It's neon, okay? And we put here neon. And after neon, we will compare elements with its structure, okay? I give you an example. So neon, and the next one will be sodium. Sodium, its number is 11. Yeah, and it's will be like neon and 3s1. What about potassium? With which noble gas we will compare its electron structure? Let's go to periodic table. Potassium is here, and the previous noble gas, the closest one is argon, okay? And we will use it here. So argon, okay, and 4s1. Iron, the same, argon, and 4s2, 3d6. this one, 4s2, 3d10, and 4p2. And this one, selenium, 4s2, 3d10, and 4p4. Sometimes when d subshell is finished, we can, don't mention it. So we can write like this for element number 32. It can be argon, and then 4s2 and 4p2, and that's all. So sometimes, or very often, you don't need to write down like 3D subshell if it is finished. Okay. Other thing that I want you to appreciate, based on what we just learned, is pattern in the periodic table of elements. And you can see it here. It's the picture symbolized periodic table, and you can see that electron configurations can be predicted by the position of an atom in the periodic table, because the shape of periodic table mimics the filling of the subshells, subshells with electrons. Each element with S subshell being built locate in the 1A and 2A groups of periodic table, right? And we can see it here. So hydrogen, lithium, beryllium, sodium, magnesium, potassium, calcium. So it will be S block. Okay, but don't forget about helium. It's a kind of exception, and it locates in 8A group, but it also has block element. Each element with the p subshell building located at the 3A, 4A, 5A, 6A, 7A, and 8A groups, or you can name it 13 through 2A18. It's P block. So the last 6 elements of each period is P block. Only first period has no p elements at all, but every other has. And transition groups from 3b to from 3 to 12 are D element or D block, and they are 10. And at the bottom, 2 rows here, out of 14 elements in each, it's F elements. And in your handout, there are a picture which shows that using periodic tables is very easy to predict, to tell what subshell is going to be filled. Okay? Okay, let's go on. The chemical properties of elements are mostly due to the valence electrons, which are the electrons in their outermost energy level. What does that mean? For example, let's see here. Outermost energy level or outer shell, right? So if we have elements from the period number 2, like lithium or boron or carbon, right? So the outer shell will be the second shell, the shell number 2. For elements like potassium, which is element of period number 4, the outer shell will be 4th, right? So also for iron, selenium, and others. And electrons which are located on their farthest energy level, they are less attracted to the nucleus. That's why they are easy to manipulate. And in chemical reactions, elements are manipulating their electrons, they gain or they lose their electrons to become more stable. And what does that mean, become stable? Now we reach to the octet rule. So what does that mean? That means that atom is stable when it has 8 electrons for most of the atoms, 8 electrons on its outer shell. Okay, so neon, why it is stable? Why it is noble gas? Because it has 8 electrons on its last energy level, energy shell, right? Why helium is stable too? And this is an exception. It's an element from the first period, so it will be stable only with having 2 electrons. Let's go here, argon. Argon, krypton, xenon, and radon. So they are all noble gases, and they all will have finished, completed outer shell. They all will have 8 electrons there. And every other atom wants to be like them. That's why when they react with with other elements, they gain electrons or they lose electrons, and they tend to become with electron structure like noble gases. Okay, but there is a definition like valence electrons. Valence electron. A valence electron, and we will use periodic table to define how many valence electron every atom has, right? So not only number of shells periodic table shows us. Also, it shows us a number of valence electron. For example, this picture shows us that for main groups from 1 to 8, the number of valence electrons for each atom equals to the group number. For example, for all elements from 1A group, they have 1 valence electron, and for elements from 2nd A group, they have 2 valence electron, and so on. 5 group, 5 valence electrons, 6 groups, 6 valence electrons, 7 group, 7 valence electrons. Why there are dots here? What did I do? Okay. Why dots are here, right? So dots here because okay, not like this, sorry. Dots are here because they symbolize a valence electron. So 1 dot symbolizes 1 electron, and we remember that in every on every orbitals can be a maximum 2 electrons. So it can be if maximum amount of valence electrons is 8, so that's why each of noble gases can be rounded with 4 pairs of valence electrons, right? So you can do this 1 pair, 2 pair, 3, and 4. Together it's 8 electrons, okay? But how you can write down its dot structure, Lewis dot structure, when it's less than 8 electrons? I will suggest just imagine. Yeah, I would suggest it will be like this. If it has 3 or 4 or 5, just start with this, like let's do this, like let's do sodium, then magnesium, then aluminum, then silicon, then phosphorus, okay, then sulfur, chlorine, and argon. Okay, so sodium, element group number 1, so it has 1 valence electron, and you put 1 dot here, or anywhere but near to the symbol. Okay, magnesium has 2 valence electron because it is from group number 2, so 2 dots. Okay, aluminum will have 3 dots, 1, 2, 3, and as you can see, there are no pairs, okay, because 4 pairs, and you need to fill 4 spots around the atom, and after you can put additional dots to make it pairs, okay. For silicon, it will be 1, 2, 3, 4, but for phosphorus, it will be 1, 2, 3, 4, and 5. So 1 pair. Okay, for sulfur, it will be 1, 2, 3, 4, 5, and 6. For chlorine, it will be 1, 2, 3, 4, 5, 6, and 7. And for argon, it will be 1, 2, 3, 4, and then 5, 6, 7, and 8. And 8, 4 pairs. Okay. I will not grade well as you write like this. 1, 2, 3, 4, 5. Okay, just tend this principle. 4 spots around the atom. Okay. And now move on to concept checking. You need to answer the questions and we can do it together. Sulfur. So you please use periodic table. So sulfur. And now you know why you need these symbols of elements, because you know how to pronounce them, you know how to symbolize each element. Okay, so sulfur, its symbol is S and its atomic number is 16. Okay, and let's jump here. So sulfur, I would write S 16 here, and mass number, it will be 32.07. Why it is fractional? 32.07 because it's average mass between existing isotopes of sulfur. Okay, so we need to define a number of protons and the number of electrons, and you know that atomic number shows us the number of protons, 16, that means 16 protons, and in atom number of protons equals to number of electrons, so it's 16 electrons here. What is the average relative mass of this atom? And you will use this number 32.06. is it metal and non-metal or a metalloid? And you know that this is a staircase and all elements to the right are non-metals. So sulfur is there, so it is non-metal. Use your answers to part C to help you answer the questions below, and you will need to remember a property of metal and metals and non-metals. So how well does it conduct heat? It is non-metal, so not well. How well does it conduct electricity? It is non-metal, so not well. Does it bend or shatter in a solid state when it is hit with a hammer? It is non-metal, that's why it shatters. Which another element behaves most like it? How to find the answer for this question? Jump to periodic table, okay? And this is sulfur, okay? Sulfur. And elements above and below the sulfur will be the most similar to the sulfur element. So you can see it's oxygen and selenium here. So yes, and you will write it here, oxygen and selenium. But if you think more, you would prefer selenium because it's solid, just like sulfur. And oxygen is a gas, that's why it's less similar to sulfur. But both answers will be good. Okay, so how many valence electrons does each neutral atom have? Each neutral atom have. For sulfur, it is 6 electrons because sulfur is from 6a group, so 6 valence electrons. Okay, how many core electrons? Core electrons are others except of valence, so it's 16 total. 6 valence, that means 10 core electrons. Draw the full electron configuration, and you will use 1s2, 2s2, 2p6, 3s2, 3p4, and you can see outer shell has 6 electrons, 6 valence electrons, exactly like the group number, okay? And draw the abbreviated electron configuration. For drawing abbreviated electron configuration, we need to find previous noble gas which ends previous period. So it's neon, right? Neon. And neon has 10 electrons. 10 electrons. So this is neon configuration. Why? Because 2, 2, and 6 gives us 10 electrons exactly. So we can draw neon, yeah, and 3s2 and 3p4 electrons, which how to say more than neon has. Okay. Draw the Lewis dot structure of this atom, and you know how to do this. So 6 valence electron, we start with 1, 2, 3, 4, and then do pair 5, 6. Okay, that is the good example of Lewis dot structure. The next element is calcium. Use information from the periodic table to get the number of protons and the number of electrons, the same question. So find calcium here, its number is 20. So we write down it here 20 and 40.6. I don't remember. Let's take a look again. 0.8. It's fractional too. 0.8 because there are several existing isotopes of calcium and its average mass of this element. So 20 gives us a number of protons 20, a number of electrons 20. What is the average relative mass? We use this, the biggest number, 40.08. Is it metal, non-metal, or metalloid? Go to periodic table again. This is staircase, and this is stairs, and calcium is to the left, so and it's in blue, so it's metal. Okay, use your answer to part C to help you answer the question below. And it is metal, and we remember metal properties. How well does it conduct heat? It is metal, so well. How well does it conduct electricity? It is metal, so well too. Does it bend or shatter? Yes, it is bent because it's metal. Which another element behaves most like it? And you know, above and below. Magnesium and strontium, and I will use both of them. So magnesium and Sr. How many valence electrons does each neutral atom have? Calcium, jump to periodic table, group number 2A. That means the number of valence electrons is 2. Okay, 2 valence electrons, and core amount of electrons, total amount of electrons is 20. 2 valence, that gives us 18 core electrons. Okay. Draw the full electron configuration, and you know how to do that. To use the order which was given to you, 3s2, 3p6, and 4s2. And you can check yourself by adding subscripts. And you need to get 20 electrons, right? 2, 2, and 6, 10. 2, 6, and 2, 10. Another 10, so it's 20 together, so we are right. And outer shell electrons are here on the 4th shell. So, and calcium is in a period number 4, so we are good. We did a great job. Draw the abbreviated electron configuration. For abbreviated electron configuration, we need previous noble gas. So calcium, go back, and we can see the previous one, noble gas, is argon. Okay, it has 8 electrons, and you can see this is argon configuration. Okay, so it will be argon here. And what is the difference between argon's electron configuration and calcium? It's here, 4s2. Okay, draw the Lewis dot structure of this atom. So, and you know how to do that? How many dots we need to draw? 2, because it has 2 valence electrons. So 1 and 2 go to the other side, 2. Okay. What group does it belong to? Common name for the group of elements. Oh, and you need to go back to the first maybe part of lecture. It's earth, alkali, okay, alkali, metals. Okay, so I think we're done here, and you will need to finish practice to complete this table, practice problem set 3 by yourself. We went through all examples, so you will be good to do this. And don't forget to complete, scan, and download these handouts to let me see it, okay? And I wish you good luck and see you in the class.